Welcome to the series of e-learning modules on linear programming problems, Charnes M technique without proof. At the end of this session, you will be able to explain the significance of artificial variable technique, explain the concept of the big M method, explain the iterative procedure of the big M method algorithm, explain inserting of slack, surplus, and artificial variables, explain two-phase method that solves linear programming problems in two phases. Let us start with an introduction. In certain situations discussed below, it is difficult to obtain an initial feasible solution. They arise when the constraints are of the less than or equal to form, then summation aij xj is less than or equal to bi, where xj is greater than equal to 0. But some right-hand side constraints are negative. That is, bi is less than 0. Then, in this case, after adding non-negative slack variable si, where I is equal to 1, 2, 3, up to m, the initial solution so obtained will be si is equal to minus bi for some I. It is not the feasible solution because I violates the non-negativity condition of slack variables, that is, si is greater than or equal to 0. When the constraints are of the greater than equal to form, then summation aij xj is greater than or equal to bi, xj is greater than equal to 0. In this case, to convert the inequalities into equation form, adding surplus, negative slack, variables, summation aij xj minus si is equal to bi, xj is greater than or equal to 0. Letting xj is equal to 0, where j is equal to 1, 2, 3, up to n, we get an initial solution minus si is equal to bi or si is equal to minus bi. It is also not a feasible solution as it violates the non-negativity conditions of surplus variables, that is, si is greater than or equal to 0. In this case, we add artificial variables ai, where I is equal to 1, 2, up to m, to get an initial basic feasible solution. The resulting system of equations, summation aij xj minus si plus ai is equal to bi, xj, si and ai is greater than equal to 0. I is equal to 1, 2, up to m, has m equations and n plus m variables, that is decision variables, m artificial variables and m surplus variables. An initial basic feasible solution of the new system can be obtained by equating n plus 2m minus m is equal to n plus m variables equal to 0. Thus, the new solution to the given linear programming problem is ai is equal to bi, where I is equal to 1, 2, up to m, which does not constitute a solution to the original system of equations because the two systems of equations are not equivalent. Thus, to get back to the original problem, artificial variables must be driven to 0 in the optimal solution. There are two methods for eliminating these variables from the solution. They are the two-phase method and the big M method, or the method of penalties. Following are the remarks. Artificial variables are only a tool to get the simplex method started. These variables will eventually be equated to zero in the solution in order to attain feasibility in the original problem. These variables are added to those constraints with equality and greater than or equal to sign. Let us now discuss about two-phase method. In the first phase of this method, the sum of the artificial variables is minimized subject to the given constraints to get a basic feasible solution of the linear programming problem. The second phase minimizes the original objective function starting with the basic feasible solution obtained at the end of the first phase. Since the solution of the linear programming problem is completed in two phases, this is called the two-phase method. Advantages of this method: no assumptions on the original system of constraints are made, that is, the system may be redundant, inconsistent, or not solvable in non-negative numbers. It is easy to obtain an initial basic feasible solution for phase 1. The basic feasible solution, if it exists, obtained at end of phase 1, is used to start phase 2. Steps of the algorithm are as explained below. Phase 1. Step 1. If all the constraints in the given linear programming problem is less than or equal type, then phase 2 can be directly used to solve the problem. Otherwise, a sufficient number of artificial variables are added to get a basis matrix, that is, identity matrix. If the given linear programming problem is of minimization, then convert it to the maximization type by the usual method. Step 2. Solve the following linear programming problem by assigning a coefficient of -1 to each artificial variables and 0 to all the other variables in the objective function, and with the basic feasible solution x1 equal to x2 is equal to xn is equal to 0 and ai is equal to bi, where I is equal to 1, 2 up to m. Maximize z star is equal to summation of -1 a subject to the constraints summation of aij xj plus ai is equal to bi, where I is equal to 1, 2 up to m. Xj, ai is greater than equal to 0. Apply the simplex algorithm to solve this linear programming problem. The following three cases may arise at optimality. Maximum z star is equal to 0 and at least one artificial variable is present in the basis with position value. Then no feasible solution exists for the original linear programming problem. Maximum z star is equal to 0 and no artificial variable is present in the basis. Then the basis consists of only decision variables x, j, s, and hence we may move to phase 2 to obtain an optimal feasible solution to the original linear programming problem. Maximum z star is equal to 0 and at least one artificial variable is present in the basis at 0 value, then a feasible solution to the above linear programming problem is also a feasible solution to the original linear programming problem. Now, in order to arrive at the basic feasible solution, we may proceed directly to phase 2 or else eliminate the artificial basic variable and then proceed to phase 2. Once an artificial variable has left the basis, it has served its purpose and can therefore be removed from the simple table. An artificial variable is never considered for re-entry into the basis. Remark: the linear programming problem defined above is also called auxiliary problem. The value of the objective function in this problem is bounded from above by 0 because the objective function represents the sum of artificial variables with negative unit coefficients. Thus, the solution to this problem can be obtained in a finite number of steps. Phase 2. Step 3. Assign actual coefficients to the variables in the objective function and 0 to the artificial variables which appear at 0 value in the basic at the end of phase 1. That is, the last simplex table of phase 1 can be used as the initial simples table for phase 2. Then apply the usual simplex algorithm to the modified simplex table to get the optimal solution to the original problem. Artificial variables which do not appear in the basis may be removed. Following is the explanation on the Big M method. The Big M method is another method of removing artificial variables from the basis. In this method, we assign coefficients to artificial variables undesirable from the objective function point of view. If objective function z is to be minimized, then a very large positive price called penalty is assigned to each artificial variable. Similarly, if z is to be maximized, then a very large negative price, also called penalty, is assigned to each of these variables. The penalty will be designated by -m for a maximization problem and +m for a minimization problem, where m is greater than 0. The Big M method for solving an linear programming problem can be summarized in the following steps. Steps of the algorithm are as follows. Step 1. Express the linear programming problem in the standard form by adding surplus variables and artificial variables. Assign a 0 coefficient to surplus variables and a very large positive number +m minimization case and -m maximization case to artificial variable in the objective function. Step 2. The initial basic feasible solution is obtained by assigning 0 value to the original variables. Step 3. Calculate the values of Cj minus Zj in last row of the simplex table and examine these values. If all Cj minus Zj is greater than equal to 0, then the current basic feasible solution is optimal. If for a column K, Cj minus Zj is most negative and all the entries in this column are negative, then the problem has an unbounded optimal solution. If one or more Cj minus Zj is less than 0, select the variable to enter into the basic with the largest negative Cj minus Zj value, that is Cj minus Zj is equal to minus 3 is equal to minimum of Cj minus Zj, where Cj minus Zj is less than 0. The column to be entered is called key or pivot column. Step 4. Determine the key row and key element after identifying the variable to become the basic variable. The variable to be removed from the existing set of basic variable is determined. For this, each number in XB column, that is BI values, is divided by the corresponding but positive number in the key column, and a row is selected for which this ratio, constant column by key column, is non-negative and minimum. This ratio is called the replacement or exchange ratio, that is XBR by ARJ equal to minimum of XBI by ARJ, where ARJ is greater than 0. This ratio limits the number of units of the incoming variable that can be obtained from the exchange. It may be noted here that division by a negative or by a 0 element in key column is not permitted. Remarks: at any iteration of the simplex algorithm, any one of the following cases may arise. If at least one artificial variable is present in the basis with 0 value and the coefficient of m in each Cj minus Zj, where j is equal to 1, 2, up to n value is non-negative, then the given linear programming problem has no solution. That is, the current basis feasible solution is degenerated. If at least one artificial variable is present in the basis with positive value and the coefficient of m in each Cj minus Zj, where j is equal to 1, 2, up to n, value is non-negative, then given linear programming problem has no optimum basic feasible solution. In this case, the given linear programming problem has a pseudo-optimum basic feasible solution. Let us take an example to understand the solving of a linear programming problem using the penalty method. Solve the following linear programming problem using the penalty big M method. Minimize z equal to 5x plus 1, 3x2. Subject to the constraints 2x1 plus 4x2 less than equal to 12. 2x1 plus 2x2 equal to 10. 5x1 plus 2x2 greater than equal to 10. And x1, x2 greater than equal to 0. Solution. Introduce the slack variable s1, surplus variable s2, and artificial variable a1 and a2 in the constraints of the given linear programming problem. The standard form of the linear programming problem is stated as follows. Maximize z is equal to 5x1 plus 3x2 plus 0, s1 plus 0, s2 plus ma1 plus ma2. Subject to the constraints 2x1 plus 4x2 plus s1 is equal to 12. 2x1 plus 2x2 plus a1 is equal to 10. 5x1 plus 2x2 minus s2 plus a2 is equal to 10. And x1, x2, s1, s2, a1, a2 is greater than equal to 0. An initial basic feasible solution is obtained by letting x1 equal to x2 equal to s2 equal to 0. Therefore, the initial basic feasible solution is x1 is equal to 12, a1 is equal to 10, a2 is equal to 10, and minimum z is equal to 10m, plus 10m is equal to 20m. Here it may be noted that the columns which correspond to the current basic variable and from the basis identity matrix are S1, slack variable, A1 and A2, both artificial variables. The initial basic feasible solution is given in table. Cj is equal to 5, 3, 0, 0, m, m. The coefficient of basic variable Cb is equal to 0, m, m. Variables in basis B are S1, A1, A2. The solution values B equal to xb are 12, 10, 10. The variables x1 are 2, 2, 5. The variables x2 are 4, 2, 2. The slack variable S1 are 1, 0, 0. The surplus variable S2 are 0, 0, minus 1. The artificial variable A1 are 0, 1, 0 and A2 is 0, 0, 1. Since the value C1 minus Z1 is equal to 5 minus 7m is the smallest value, therefore x1 becomes the entering variable. To decide which basic variable should leave the basis, the minimum ratio is calculated as 12 by 2, 10 by 2 and 10 by 5, which is nothing but xb by x1. Zj is calculated by multiplying the x1 variable and the coefficient and taking their summation. So in the x1 column, we will get 0 into 2 plus m into 2 plus m into 5 is equal to 7m. Similarly, we will get the Zj value of the other column as 4m, 0 minus m, m and m. In the next row, we calculate the values of Cj minus Zj, which is equal to 5 minus 7m, 3 minus 4m, 0, m, 0 and 0. Iteration 1. Introduce the variable x1 into the basis and remove a2 from the basis by applying the following row operations. The row solution is shown in the table below. R3 new is given by R3 old by 5. R2 new is given by R2 old minus 2R3 new. R1 new is given by R1 old minus 2R3 new. Then we get the new table with the following values. The coefficients are 0, m and 5. The variables in basis are S1, A1 and X1. The solution values are 8, 6 and 2. The Cj values are the same. The values of X1 variable are 0, 0 and 1. The values of X2 variable are 16 by 5, 6 by 5 and 2 by 5. The values of S1 are 1, 0 and 0. The S2 values are 2 by 5, 2 by 5 and minus 1 by 5. The values of A1 are 0, 1 and 0. The minimum ratios are 8 divided by 16 by 5, 6 divided by 6 by 5 and 2 divided by 2 by 5. The values of Z are 10 plus 6m. The values of Zj are 5, 6m by 5 plus 2, 0, 2m by 5 minus 1 and m. The value of Cj minus Zj are 0, minus 6m by 5 plus 1, 0, minus 2m by 5 plus 1 and 0. Iteration 2. Introduce variable x2 into the basis and remove s1 from the basis by applying the following elementary row operations. The new solution is shown in the table below. R1 new is given by R1 old into 5 by 16. R2 new is given by R2 old minus 6 by 5, R1 new. R1 new is given by R3 new minus R3 old minus 2 by 5, R1 new. We will get the table with the following values. The coefficients are 0, m and 5. The variables in the basis are x2, a1 and x1. The solution values are 5 by 2, 3 and 1. The Cj values are the same. The values of x1 variable are 0, 0 and 1. The values of x2 variable are 1, 0 and 0. The values of S1 are 5 by 16, minus 3 by 8 and minus 1 by 8. The S2 values are 1 by 8, 1 by 4 and minus 1 by 4. The values of A1 are 0, 1 and 0. The minimum ratio are 5 by 2 divided by 1 by 8, 3 divided by 1 by 4. The values of Z are 5 plus 3m. The values of Zj are 5, 3, minus 3m by 8, m by 4 and m. The values of Cj minus Zj are 0, 0, 3m by 8 minus 5 by 16, minus m by 4 plus 7 by 8 and 0. Iteration 3. Introduce S2 into the basis and remove A1 from the basis by applying the following new operation. R2 new is given by R2 old into 4. R1 new is given by R1 old minus 1 by 8 R2 new. R3 new is given by R3 old plus 1 by 4 R2 new. We will get the table with the following values. The coefficients are 3, 0 and 5. The variables in the basis are x2, s2 and x1. The solution values are 1, 12 and 4. The Cj values are the same. The values of x1 variable are 0, 0 and 1. The values of x2 variable are 1, 0 and 0. The values of S1 are 1 by 2 minus 3 by 2 and minus 1 by 2. The S2 values are 0, 1 and 0. The values of A1 are minus 1 by 2, 4 and minus 1. The value of Z is 23. The values of Zj are 5, 3, minus 1, 0 and 7 by 2. The values of Cj minus Zj are 0, 0, 1, 0 and m minus 7 by 2. From the above table, it is observed that all Cj minus Zj is greater than equal to 0. Thus, an optimal solution has arrived at with value of variables as x1 is equal to 4, x2 is equal to 1, s1 is equal to 0, s2 is equal to 12, and minimum z is equal to 23. Summary. Here is a summary of our learning in this session, where we have understood the significance of artificial variable technique, the concept of the Big M method, the iterative procedure of the Big M method algorithm, the inserting of slack, surplus, and artificial variables, the two-phase method that solves linear programming problems in two phases.